And wow, we got a pretty good crowd tonight. That's really nice. Let's see if Jason is here.
Advertising.
Hello.
Yeah, Jason, if you're in this group, can you let us know?
Can you hear me?
Yes, I see
Yeah,
him.
I can.
JW.
All right.
Got it. Yeah, and I can
yeah,
see you too.
I
Looks
just
like
got
you're out
in.
at one of the observatories.
I'm virtually on
You're virtually
Mauna
out,
Kea
huh?
in
Yeah.
Hawaii. I'm actually observing tonight in a couple hours. So
Yeah, right. Well, that's really neat, and we're really interested in understanding what you do.
What's your target for tonight?
we have depends on the weather. So there's a chance of snow on the summit. So depending on whether depending on how bad the weather is, our targets will vary. So our goal is to do spectroscopy of exoplanets, planets orbiting other stars, study their atmospheric composition. But depending on how many clouds and if there is snow, we have to close the telescope and things like that. We may try easier targets than exoplanets.
Yeah, great. Is the snow on the ground, or are they expecting snow at the site?
There's currently no accumulation, so they're just worried about it precipitating in at night, basically.
Yeah, so you might get snowed out, huh?
Yeah, yeah. So we'll see how it goes. The last couple of nights it was raining on the summit, and with a hint of flurries, I was told. So we'll see. Tonight looks slightly better, but it's a very, very low bar for being slightly better than the last 2 nights.
Well, the snow's not a problem. It's the clouds that are a problem.
Yeah, but the snow usually comes out of clouds.
Well, we can't we can't have a telescope accumulating snow on its mirrors either, so.
Yeah, you can't really open the dome if you've got snow, right?
No, we need one of those glass domes so you can observe through the snow and not get accumulation.
Jason, I'd like to introduce you to Dr. Scott Dixon, who's the host tonight, and he also heads the efforts examining candidate exoplanets for the TESS program, NASA's TESS program.
Yeah.
Our organization actually does follow-up confirmation of TESS candidates. So
right.
Awesome.
Yeah, we're several of us are part of the SG1, the subgroup 1 that does the imaging from the ground with reasonable sized assets, mostly less than a meter. Although there's a lot of work that goes on with RV measurements and other things, but we certainly, we're involved in exoplanets a bit, and we all take pictures of the sky, but I don't believe there's any one of us that takes pictures of exoplanets. That's really.
Yeah, it's definitely technically challenging. So I'll describe how hard it is to do this. But so you definitely can't just bring out any old telescope and try to do this. We have to use the largest telescopes in the world.
Yeah, for sure. So we're real interested in hearing everything you have to say. The only other thing I have tonight is I ought to just say a little bit about the rest of the year. Mike Chasen, I believe next month is going to show us his observatory at TDS. And Mike, are you around? I thought Mike was going to be here, but I guess not yet. So we'll have one in November, and it's usually the 4th Wednesday of the month. That's the way we kind of schedule it. But since Mike's going to show us the observatory, if the weather doesn't look good on that particular date, we may shift it and pick a better date to do his talk on his observatory. Then we'll probably take December off, and next year, who knows what's going to happen next year. We'll see what we can put together. But with that, I guess that's all I really have to say today. So maybe we should just let Dr. Jason Wang show us how to image exoplanets, and then we can all try it, right?
Sure. All right, should I get started?
Yeah, sure. Go ahead.
All right, so let me share my screen. All right, how's that look?
You got it. At least I've got it.
Great. Yeah, so hi everyone, my name is Jason. I'm a postdoc at Caltech, so just up in Pasadena. So today I'm going to talk to you about how we take real images of exoplanets, none of the artist conception stuff that you might be used to seeing. So it's like it sounds like some of you are quite familiar in the field of exoplanets, but I just wanted to give some introduction just for everyone's sake. So let's first think about our own solar system. We have 8 planets. You might have seen some of these really beautiful pictures of the planets in our own solar system. This is a picture of Jupiter taken by the Hubble Space Telescope. You can these pictures are amazing. You can like see all the individual cloud structures on Jupiter. You can see the atmospheric dynamics going on. There's really a lot of beautiful stuff that you can learn from looking at these planets up close and in detail. And because the solar system planets are so close, we can actually fly spacecraft to them. So this is a picture taken of Jupiter with its moon Io in the foreground by the Cassini spacecraft. And images like this really are only possible in our own solar system right now. And you can really appreciate here the scale of Jupiter compared to its tiny moon Io, which is hard to do in space when you don't really have points of reference typically. So we've been able to get really beautiful pictures of all the planets in our own solar system by using either our telescopes or by flying spacecraft to them. So here you can see some images I took from the NASA website from all our 8 solar system planets. Yeah, I just sometimes take some time just to marvel at these. They're all you can see so much detail, so much about these worlds are not just individual points of light. Like some of the stars that we see up in the sky. So these are our own solar system planets. You can see them in quite great detail. So you've probably heard about exoplanets or planets orbiting other stars, and you might have seen some like news about them. So when sometimes a cool exoplanet gets discovered, you might see some picture like this. So this is a artist conception of Kepler 69c. This is a super Earth planet, sometime I think about 50% larger than the Earth. We think it's probably rocky, but we don't have an image of it. All we have basically are its mass and its radius and its orbital separation, and from that we kind of can make an educated guess about what the nature of this world is. But this is just one of many possibilities. This world that you see here looks, kind of bluish. Maybe there's liquid water or something like that on the surface. You can see these clouds, but we don't actually know because we've never actually seen into this planet. We just know that roughly based on this mass and radius that it probably should be rocky, and the only rocky-ish planets we know of are the rocky planets in our own solar system. So we just kind of extrapolate from that. And this is because there's been thousands of exoplanets discovered, but almost all of them have been discovered through indirect techniques. So these techniques don't actually measure the exoplanet directly. They measure the influence of the exoplanet on its host star. So the first technique is the transit technique. It takes advantage of the fact that a small percentage of these exoplanets just happen to lie in an orientation relative to us that it actually crosses in front of its star once per orbit. So if we monitor the light of the host star, we see these periodic dips. And from these periodic dips, we can actually infer that there has to be a presence of a planet. And from that, we can actually also measure its radius. So this is probably the most prominent method. It's discovered thousands of exoplanets. You might have heard of like the Kepler mission or the TESS mission. Those missions rely on this technique, this transit technique, and monitoring the brightness of the host star. The second indirect method is the radial velocity method. So here it relies on Newton's third law. So as the planet orbits the star, not only is the star pulling on the planet, but the planet is also gravitationally tugging the star, causing the star to wobble back and forth. So when the star wobbles towards us, the light of the star gets blue shifted, and when the star wobbles away from us, the light of the star gets red shifted. And this periodic reddening and blueing, is that a word, of the star allows us to, again, infer that that there has to be a planet tugging on the star to cause this periodic Doppler shifting. But you might be wondering, can we just take a picture of a planet? We could do this with our solar system planets. If you get these super nice pictures, we have, let's take the best telescopes in the world. Let's just try and image one. Well, direct imaging is pretty hard. So for the easiest case, the easiest exoplanets that we know of to date that we can directly image is akin to trying to watch a firefly circle a streetlight from several miles away. So that gives you a sense of both the difference in brightness, how much brighter the star is than the planet, and it gives you a sense of the angular separation, how far in the sky, how closely separated is the planet from the star. And because of both the large brightness ratio and its close separation, it's really hard to see these planets from the glare of the star like it is trying to see a firefly from the glare of a streetlight. But I wouldn't be here talking about it if we haven't done it. So we have done it. So probably one of the most famous directly imaged exoplanet systems is a system called HR 8799. That's just the name of the star. It's from some star catalog. So here you can see there's actually 4 planets around the system. The outermost planet is planet B. You can see it to your left at around 10 o'clock. And then as we discover more and more planets, we give them basically more letters in the alphabet. The star is capital A, and then the first planet is lowercase b, next one is C, next one is D, next one is E. So here we discovered 4 planets around the star. The star is actually, if you're wondering where it is, actually hidden behind what's called a chronograph. I'll talk about this in a second, but we've actually tried to block out the star's light. And the 4 planets here, you see them as kind of like circles, right? So you might be wondering, are you seeing the disk of these planets? These planets are not actually resolved. These planets are single point sources of light. And just how we image points of light on a detector, they look like large blobs, but they're actually just a single point of light. We're not able to resolve their surfaces. So how do we do this? Well, I drew a little cartoon schematic instead of showing you optical diagrams about how we do this. So generally, to do this, you have to use some of the largest telescopes in the world. Those telescopes have to be on Earth. We haven't been able to fly these telescopes yet. We want to, but we're not at that stage yet. So to image these faint planets next to their bright host stars, we have to deal with the fact that there's atmospheric turbulence. So atmospheric turbulence distorts the light. So what we have to do is then use this technique called adaptive optics to correct for atmospheric turbulence. It's like basically giving your telescopes prescription glasses, except unlike us, where we go to optometrists, say like once a year if we're good, we have to change the prescription of this adaptive optic system once every millisecond, because that's just how often the atmosphere changes. So this telescope is basically going to the optometrist every millisecond to go get a new prescription to fix the atmospheric turbulence. After our adaptive optic system, we have what we call a chronograph. This basically blocks out the glare of the star. And then behind this entire system, then we can place a camera to then take an image of this exoplanet. So I'll talk about these 2 components a bit in detail. So first, let's talk about atmospheric turbulence. The atmosphere is nice on Earth. It allows us to breathe, gives us climates, it gives us life. But it also gives us fuzzy pictures of stars. So here's an image that we've taken of a star, zoomed in, super magnified, taken without adaptive optics. So you can see this cloud, this blur of light. So this is all this blurring due to the Earth's atmosphere. So these images that I'm showing here are taken about a couple of seconds apart. So like I said, the atmosphere actually operates on millisecond timescales, but even on the second timescales, you can see the blurring of the atmosphere changing things and moving the star around is causing this giant fuzzball. But then we turn on adaptive optics by going to basically a very, very efficient optometrist. You get this image on the right. So here, that cloud of light has been concentrated into the central core. So you can see this, the star is now this very nice compact object. And if you notice very closely, there's actually a second point source in this image. This is actually a binary star system. The binary star, I think somewhere like 100 times fainter than the primary in this image. This secondary star would have been completely lost in the fuzzball of the primary star if we didn't have adaptive optics. So we would have never even known it existed without using adaptive optics to correct for the distortions of the atmosphere to give us this much better angular resolution to see these points of light as very crisp points of light and not as this fuzzy thing. So the second thing that we need in addition to adaptive optics is what we call a coronagraph. So we need something to block the glare of the star. So let's say we actually can fly a 10-meter telescope in space. So there's no atmospheric turbulence. We have this perfect image. If you take an image of a star, this is simulations because we can't fly a 10-meter telescope in space. But this is what you would see. Basically, you see all these ripples in this image. These ripples is due to the quantum nature of light. It's due to the starlight interfering with itself, creating an interference pattern. And this interference pattern kind of creates this ripply shape. And this interference pattern is actually much brighter than any planet that we know of. So there actually is a planet in the simulation I'm showing here, but you actually cannot see it because it's completely hidden underneath the glare of the star. And this glare is fundamental. It's just due to the quantum nature of light. But if we add in what's called a chronograph, it's a series of fancy optics that we can use to suppress the glare of the star. Then, assuming there's no atmosphere, we get this very nice image where the star is now been suppressed. Most of the light has been hidden underneath this mask. And you can see there's this faint planet next to the star that gets revealed that otherwise is completely unseen without a chronograph. So we need both adaptive optics and chronographs to be able to see planets. So so you might be familiar with adaptive optics. It's kind of like if you wear glasses, taking your glasses on and off, and what a difference that makes. You might be less familiar with chronographs unless maybe you've seen a solar eclipse. So a solar eclipse is essentially a chronograph in action. So here, the sun is the star we're interested in blocking the light out of. The moon is our chronograph. And during a solar eclipse, because the moon and the sun happen to be the same size in the sky roughly, the moon blocks out the light of the star, and we can actually see the solar corona, which is what the chronograph is named after. And the solar corona is all these filaments kind of being erupted out from the star that we can study. But also during a solar eclipse is one of the times that you can actually see Mercury during the day. So Mercury orbits very close to our sun, and except for during sunset and sunrise, it's really hard to see Mercury because the glare of our own sun blocks out the light of Mercury. So during a solar eclipse, because we have this moon to suppress the glare of the star, we're actually able to see Mercury during the day. So with these two pieces of technology, we're able to image exoplanets. So here's a gallery of exoplanets that we've been able to image so far. I'll note that all these exoplanets are generally quite massive. They're more massive than Jupiter. They're somewhere between 2 to 10 times the mass of Jupiter. So we call them super Jupiters. They're generally very young. They're less than about 100 million years old. I'll talk about this a bit more, but generally we image very young systems because young systems are still very hot because they've just recently formed and they're still radiating away the heat of their formation. And because they're very hot, they're much brighter and making them easier to see. And generally, all these images are taken in what's called the near infrared. So this is like slightly redder than red. We're talking, so like if you think about red as, so we're talking about like one micron-ish. So it's like about factor 2 in wavelength compared to the visible. So I'll talk about a few of these systems in particular that I've worked on that I think are interesting. The first one I'll talk about is 51 Ari B. So 51 Ari is the star. So you can see in this image, the star is behind the chronograph, behind this X, behind the cross. And then 51 Ari B is at the bottom at about 6 o'clock. You can see this bright dot. This is real data that we took, and you can see the light emanating from this planet. So we took this image using the Gemini South telescope. So Gemini South is an 8-meter telescope. It's in Chile on Cerro Patron. It's at about elevation of 9,000 feet. So you can see roughly where in Chile it is. And here's a picture I took one day while walking up to the summit of the telescope to go observing. If you gives a sense of scale for how big these observatories are. The instrument we use is called the Gemini Planet Imager. As the name suggests, it's an instrument on Gemini telescope designed to image planets. Very straightforward. It's a series of 3 blue boxes that you'll see here. So here is an image of the Gemini South primary mirror. There's a few people at the bottom for scale. You can see just how big this telescope is. This is a 8-meter diameter telescope. I don't recommend trying to move it manually. It's really heavy. And then GPI, the Gemini Planet Imager, is bolted in the back at the cascading focus. So you can see here, now the telescope is pointed upwards, and behind the primary mirror at the very bottom is our instrument GPI, the Gemini Planet Imager. So GPI, like our cameras, actually take color photos. So if you ever thought about taking photos with a camera, you get, say you go to UC Berkeley, where I did my PhD, and you take a picture of its campus, you can get a nice picture like this. What your camera actually did was actually take 3 separate photos at 3 separate wavelengths. So it took a blue photo at the shortest wavelength. It took a green photo at a medium wavelength and a red photo at a very long wavelength, and combine them together to create the color that we see here. And we use this color to be able to distinguish things. Like, for example, the grass is green. So if you go look at the green photo, you can see the grass is very bright in the green photo. This allows us to tell us what's grass versus what's building versus what's roof versus what's sky. So GPI is like that, except instead of taking 3 colors, we take 37 colors, and the 37 colors that we take are in the near infrared. So here you see an animation we're kind of flipping through all 37 different colors that we're taking images in. So in the left, there's an arrow pointed to the location of the planet, 51 Ari B, and you can see at the bluest wavelengths, about 1.5 microns, the planet is very faint. This is because of water absorption in its atmosphere. And then as the water absorption disappears at about 1.6 microns, the planet peaks up and suddenly shoots up in brightness. You can see it's really bright there, and it comes straight back down because that's the wavelengths where methane absorption turns on. Beyond 1.65 microns, methane absorption in the planet's atmosphere turns on and makes the planet very dim again. So by taking these images as these 37 different wavelengths, we can actually study the atmosphere composition. We can show that there's both water and methane in this planet's atmosphere, and try to learn what exactly is the nature of this world. And from that, we're able to infer this is this is about a 2 Jupiter mass planet. Is very consistent with our models for what a 2 Jupiter mass planet should look like. It's very much a scaled up version of our own Jupiter. We also, in addition to be able to take images as a function of wavelengths, we can also take images as a function of time. So here's a time lapse of the planet 51 Ari B in motion. This is a time lapse of 4 years of data that we've taken with the Gemini South telescope. You can see this planet is kind of arcing or inwards. It has an orbital separate distance about 13 AU, and we're still, you can see it has orbital periods of a few decades. So we're still actively monitoring the orbit of this planet to study exactly its orbital trajectory to understand its dynamical interactions in the system. The next planetary system I'll talk to you about is was first discovered at by the Keck telescopes on top of Mauna Kea on the Big Island of Hawaii. This is actually where I'll be observing tonight. So it was discovered, on top of Mauna Kea at about 13,000 feet, there's several observatories. Two of them are the twin Keck observatories. These are both 10-meter in diameter telescopes. Today I'll be talking about the Keck 2 observatory, which is this one. I think it's that one in my background. Using this 10-meter telescope, that's how we discovered the four planets around HR 8799. These planets are also super Jupiters. These are more massive than 51 Area B. So 51 Area B, we think is about 2 Jupiter masses. These ones we think are somewhere between 5 to 9 Jupiter masses. So quite massive planets. Again, by monitoring the system over the last 7 years, we've been able to watch these planets move. This movie that we made, I think, is really spectacular because with these 4 planets, you can really see Kepler's laws of planetary motion in action. So the closest in planet, planet E, you can see it moves quite fast compared to the outermost planet, planet B, since Kepler's law says that inner planets orbit at shorter orbital periods. And this is one of the few times that we can actually see, gravity really in action in our own solar system, because we're kind of inside our solar system. It's hard to watch the planets in our own solar system orbit. They orbit weirdly because our Earth is also orbiting and everything is kind of orbiting together. Whereas here you get this nice picture where you get this top-down bird's eye view of these planets kind of orbiting their star. These planets orbit somewhere between 15 and 70 AU from their stars. They have orbital periods somewhere between 40 and 400 years, just for reference. One of the things I've worked on this system in particular is to study their dynamical history. One cool fact about this system is that it's about 40 million years old, which might sound like a lot of years, but it's actually pretty short in geological time. If you think about the dinosaurs roamed the Earth hundreds of millions of years ago and went extinct around 65 million years ago in some big mass extinction event. 20 million years after the dinosaurs went extinct, the planetary system HR 8799 was born. So this system was actually younger than the dinosaurs. So that gives you a sense for just how young this planetary system is. And we can actually use this age to kind of constrain the orbits of these planets. So we know that these planets must have been living for the last 40 million years. We can actually run dynamical simulations, so we can start off with these 2 different orbits that fit our current data and test whether they're dynamically stable for the last 40 million years. So as you can see, we're going to rewind time using gravitational simulations and basically try to assess which of these orbits are stable. It looks like my PowerPoint might be a little bit lagging, so I apologize if that is the case. But basically, we're just rewinding these planets backwards in time, and we keep going to basically look to see if one of these systems will go unstable. Let's see if this works. Yeah, it's a little slow, but the gist is that in the right simulation, basically these planets get more and more unstable until basically these planets actually kick themselves out of the system. And we know that that's an unphysical system, because if we rewind backwards in time, we shouldn't rewind it in such a way that the planets kick themselves out. They shouldn't come from infinity and just gather gathered into a planetary system. They probably formed there. So the orbital configuration on the left is much more likely because they're very stable for the last 40 million years. So with this, we're actually able to constrain the orbital parameters of the system. So here's our current best knowledge of the orbital trajectory of these 4 planets. So you can see I've overlaid on top of these this image of the 4 planets, their orbital trajectories. We think you can see that there's still some uncertainty. There's definitely a width to each of these trajectories. So we're still working on monitoring their orbits to understand better exactly their orbital configuration and understand exactly how they landed into this orbital configuration. But you can see here, this is one of the things we do with our images of planets, that these that we can actually watch these planets move and trace out their orbits to study their dynamical histories. I'd like to end with maybe a question about, so I first started showing you these beautiful images of the solar system planets where we get up and close and see great details to really study these planets as worlds rather than just single points of light. You might ask, when can we get images like these for the thousands of exoplanets that we know of? Well, to do that, you need a really large telescope. Unless we can somehow, get faster than light travel, we'll need a very large telescope to get nice resolved images of planets like this. Our current largest telescopes are about 10 meters in diameter. We will need a telescope about 10 kilometers in diameter to get images like these of exoplanets. Maybe something in the far future to think about, but unlikely that anytime soon we'll be able to obtain images like these of exoplanets. So, but we still have some pretty beautiful images of exoplanets to date. So I'll just leave up, here's a gallery of some movies I made of exoplanets in motion, and that you can take a look at. And I'll take any questions if anyone has any questions. Thanks.
Well, very good, Jason. I had generated a few questions in my head, but why don't I let somebody else go first? Anybody want to be first?
I'll ask a question. The near-IR imaging, is that done with what detector material?
I cannot remember the exact detector material off the top of my head, but they're all done with the same detector array as these things called H2RGs, but I don't remember exactly if you're familiar with that terminology for infrared detectors, but I don't remember exactly what materials they were made out of.
What did you say you referred to it as?
They're all branded. They're all these teledyne detectors, which are labeled H2RG.
I don't recognize that.
Yeah, it's they definitely have there's restrictions on who can obtain these, and there's definitely like restrictions on who can even work on them and things like that. But so they're somewhat they're somewhat restricted due to the fact the military also uses them, I think. But generally in astronomy, those are the ones that we use for these infrared imaging cases nowadays.
Okay. The silicon pin diode.
I have a question.
Go ahead, Anna.
Hi. I maybe it's somewhat connected to that last question. I'm not quite sure because I didn't hear it clearly, but I remember that slide with the 51 ARI B.
Mm-hmm.
You said you use color images to determine atmospheric compositions. Like, could you just like sort of describe what that process looked like? I mean, and you said like you take images at different wavelengths, but I forgot which like wavelengths. Was that the infrared or?
Yeah, it's a good question. So it's in the infrared. So essentially what we do is we measure the brightness of the planet at each of these wavelengths, because we can take them at 37 different wavelengths. We can measure its brightness. So you can see that on the right here is a plot of the planet's brightness as a function of wavelengths.
Yeah.
And you can see that at the shortest wavelengths, the planet is pretty faint. At the longest wavelengths, the planet is pretty faint, and we can basically correlate that with spectral features in the atmosphere.
So like if I was like, okay, I'm going to target this exoplanet, got good, you know, it's good clear night sky, whatever, and all that. And like I do the same thing and I see those dips, the dimness at those wavelengths, and I could assume the same thing. Is that how it works?
Yeah, generally there's occasionally degeneracies between what molecules can cause the same dips. So you want to make sure you have the right spectral resolution, or make sure that that your model is physical. So like things like carbon monoxide and things like that can also and not at this exact wavelength, but at 2 microns, carbon monoxide and water have actually kind of similar spectral regions of absorption. So you got to be careful about, depending on what temperature the atmosphere is at, it could either be carbon monoxide or methane that's actually responsible for the absorption.
Yeah, and how do you describe this method? Like what's the general description of what this is?
It's generally just called, I think it's just called atmospheric modeling for exoplanets.
Atmospheric modeling. Oh, okay.
Yeah, or atmospheric characterization, or exoplanet spectroscopy. Essentially, we're trying to get spectra of these exoplanets.
Okay, I think that's what I was like looking for. I was like, isn't that? And so what did you use to get these detections?
What do you mean?
Like what instruments did you use to do this? Like, did someone else ask that? I'm not quite sure.
Yeah, so for this one in particular, so there's multiple instruments that do these things. For this one in particular, we use this instrument called the Gemini Planet Imager.
Planet Imager. Oh.
Oops, I got it here. This slide.
Oh.
Yeah. So inside of this Gemini Planet Imager is both is the ability to separate this light into these 37 different spectral channels, and we're able to take an image at all of 37 spectral channels.
And where is that at? Oh, sorry.
Go ahead, Anna.
And it's located in Gemini South, which is it's an 8-meter telescope in Chile.
Okay, I thought that was it. Okay, sorry, I just didn't make that connection quick enough. So that's how I was confirming. And so is that like the same tactic of like trying to detect like life on different exoplanets, like when they detected what's that in Venus, what do they find again?
The detection of phosphine. Yeah, so the general technique of spectroscopy is similar. In the Venus case, Venus is pretty easy because it's so close to us to do a spectroscopy of Venus, whereas for these exoplanets we have to really block out the glare of the star, which is really the key challenge. But otherwise, yes, spectroscopy, or we're all doing spectroscopy to really identify the different molecular features that compose an exoplanet.
Oh, okay, thank you.
Jason, I have to, after talking about the spectroscopy, I have to ask what kind of an instrument that is, and how the light is separated into the different channels.
Right. So if you're familiar with astronomical spectrographs, it's called what we use is called integral field spectrograph. So what we actually do is first basically disperse the light into individual pixels, and then each pixel goes through a prism. And so basically we get for every pixel of this image of 51 Arri, where is it? For every pixel of the image on the left, we actually, on our raw data, is actually a spectrum of every individual pixel. And so that's how we're able to reconstruct an image that has 37 different channels. We actually take the image, decompose it into pixels, and then disperse each pixel into a spectrum. And it's a technique called integral field spectroscopy.
Right.
Is the dispersion done with a prism or a grating, or?
Yeah, it's done with a prism in this case.
Okay.
So what's the process for calibration there? That's always hard.
So the wavelength calibration is not too hard for our requirements. We just use like arc lamps that have very specific emission lines to calibrate in wavelengths. The hardest part of all of this is removing the bright glare of the star. So you might have noticed in like the first 51 Area image I showed you, there's this point source at the bottom that's B, but then you also see all this like other like light everywhere else. This isn't like real astrophysical flaring or other stuff going on. This is all residual starlight that we couldn't quite remove. So we've probably subtracted about 100 times the original starlight in this image in post-processing to see this planet. So the hardest part of the calibration is actually calibrating out the light of the star.
Yeah, I guess with the image shows in the distance in astronomical units. Can you translate that into angular resolution? How far?
Yeah, so
how big
this
is
B
the orbit?
is about 0.4 arc seconds from the star, and it's about 500,000 times fainter than the star. To give you a
So
sense
you're
for
getting with the instrument and the AO, you're getting better than better or around 1/10 of an arc second, or maybe better.
yeah.
than
So
that.
we actually get about 0.05 arc second angular resolution with our depth of optics. Yeah. And so that requires both having good depth of optics, but also having the largest telescopes in the world. Because if you go to a smaller telescope, then all of this stuff just your resolution just gets worse and worse and worse, and you just end up not being able to see anything.
What was the image size again?
For this image?
Right, yes.
So this image is about 2 arc seconds across. The planet, wait, I have to, it's about one, it's cropped, so I have to remember. This image is about 1 arc second, about 2 arc seconds across. Sorry, but the planet is about 0.4 arc seconds from the star.
That's a lot of spectrometers all in one image there.
That's right.
Wow.
We
Yeah,
also have
it's
some questions in the chat for you.
Oh, great. I can.
Well, are there questions in chat?
Let's see. Do I know Alex Filipenko, a professor at UC Berkeley? Yeah, I do know him. He's still there, obviously. I did my PhD there. We work in different fields. He works on supernova, exploding stars, whereas I work on exoplanets, but otherwise, yes. Let's see. Do I know of any new technology in the future that will improve clarity on the 51 Area B image? So we're in general, direct imaging of exoplanets is a very technology-driven field. So we're constantly trying to improve technology. On the near term, we're working on better spectrographs, we're working on better adaptive optics systems to allow us to get sharper images, to allow us to get even more detail on what this planet is made out of. In the longer term, we're working on building these large ground-based telescopes. You might have heard of like the giant Magellan telescope or the 30-meter telescope. These are telescopes that are about 3 times larger than any current telescope on the ground, and that will give us much crisper images, much sharper images of these exoplanets. And it's, so William asked, what is the length of the exposure? So this exposure is about 1 hour long. Unlike a lot of like astrophotography exposures, we're not actually limited by, say, sky background noise or photon noise or detector noise, nothing like that. We're actually limited by our ability to calibrate out the glare of the star. So we actually integrate for an hour to get enough information on how this residual starlight varies and subtract that out. So that's the reason why we go for an hour is not actually because we're limited by any sort of like detector or sky background noise. We're actually limited by our ability to calibrate out the star. And that's what drives our 1 hour exposure times. Actually.
Is that exposure, 1 hour exposure, one single exposure or a series of sub-exposures?
Yeah, good question. It's a series of sub-exposures. So we generally take 1 minute exposures, and then we basically do a lot of fancy post-processing to use those 1 minute sub-exposures to calibrate out the starlight, and then combine everything together to get this 1 hour deeper exposure.
The Jason, the spectrometer that you described earlier, what's the spectral resolution of that instrument? I mean, you had about how many channels? Maybe 100 or so channels, and
Yeah,
what's
we
the
have about
resolution?
30. Yeah, so our spectral resolution for this instrument is about 50, which is what we would term pretty low resolution spectroscopy. So it's R50 in terms of lambda over delta lambda.
Yeah.
I'm currently working at Keck, and this will be working on tonight, a spectrometer that allows us to do R of 35,000 spectroscopy. So, factor of 1,000 times higher spectroscopy to see the spectra in much finer detail. But this one, which is the original discovery image, was taken at a low spectral resolution of R of 50.
So most all of your work is in the near infrared, say from 1 to 2 microns or so.
That's right.
Is there any for imaging exos? Is there any advantage to going to longer or different wavelengths?
Yeah.
Where maybe it's much more of a thermal signal or maybe even radio wavelengths. What other ways can you do this imaging?
Yeah, that's a great question. So I think so as you go to longer wavelengths, closer to like 10 microns, the planet actually gets much more favorable in brightness because these planets are, somewhere between a few hundred to 1,000 Kelvin. So at 1 micron, they're not peaking in brightness at 1 micron. They peak at brightness somewhere between 3 to 10 microns. So going to longer wavelengths helps in the fact that the planets are brighter. Going to shorter wavelengths help because of your angular resolution. The angular resolution of your optical system is better at shorter wavelengths. So going to the optical will actually improve your angular resolution. However, the problem is that the planet gets much fainter at optical wavelengths. And if you go to much longer wavelengths, your angular resolution gets worse. So the near infrared is kind of the first sweet spot in terms of having good angular resolution and pretty good planet brightness to be able to detect these planets. However, we are pushing to both directions. So 3 to 5 microns is going to longer wavelengths is something we do at Keck actually. The HR 8799 images I showed you, the other exoplanet system was the 4 planets. That was actually discovered at 3 microns. It wasn't actually discovered in the near infrared. But beyond 5 microns right now is pretty difficult with our current telescopes. So we're kind of limited to 1 to 5 microns in general for our exoplanet characterization. Where there's hope with either the upcoming James Webb Space Telescope or with future larger optical telescopes like these 30-meter class telescopes I've been talking about to go out to say 10 microns to characterize them at even longer wavelengths. And then simultaneously, people have been working on better adaptive optics systems and better instruments to go to shorter wavelengths where we can take advantage of this better angular resolution, but the fact that planets are fainter, we had to fight that. But there's also, so we're working on basically going towards both sides, and there's advantages to that, but it's kind of the sweet spot is somewhere between 1 to 4 microns right now because of both the angular
there's
resolution.
Probably not much radio emission from the planets.
Oh yeah, that's actually a good question. So people are actually at Caltech actively looking for radio emission around exoplanets. There actually was a paper out either start of this year or end of last year that was a candidate exoplanet detected in the radio. We have not been able to confirm it yet because we don't have any other way to follow up currently. I think people are working on that, but I haven't seen any results from that yet. In the radio, you're generally seeing emission due to the planet's magnetic fields. So that's what we're looking for in the radio. Like I said, this is really new cutting edge science right now. So people have been working on it, but there's no like definitive single planet that has been discovered in the radio. But it's something that is potentially promising in the next few years.
Unmute, Frank. You're mute.
There we go. What about binary stars? It seems like there's a large number of binary stars. Do you do any imaging of those?
There have been people that have worked on binary stars, not me personally, but people have tried to do direct imaging for looking for planets orbiting the binary star system. So not orbiting, it's, well, actually, let me step back for a second. Yeah, so there's people that have been like looking for close binaries, looking for planets that orbit around the close binary. There's also wide binary systems. Actually, 51 Eri is actually a wide binary system. There's actually a binary companion 3,000 AU away. There's actually two low mass stars orbiting one another in a very compact configuration, and that center of mass, that's a pair of low mass stars, is orbiting 51 Eri at about a few thousand AU separation, and inside of that orbit is the orbit of 51 Eri B around the primary star at 13 AU. So this is already a very hierarchical system.
Yes. Yeah, that makes sense. Yeah.
Okay, there's a question on the chat. Are these gas giant exoplanets? Is there significant detection of methane? So yes, these are all these images I've shown you today are gas giant exoplanets. They're all likely more massive than our own Jupiter. And 51 Eri B is I think the only, if not one of the only planet directly imaged exoplanets that has a definitive detection of methane in the atmosphere of it.
Jason, do you do anything at the Hale telescope at Palomar?
Palomar. Me personally, I have not had a chance to do that, but I have some colleagues that do work on the Hale telescope. I think currently they're working on exoplanet instrumentation to more indirect technique in exoplanet instrumentation. There's techniques to study the planets through transits and through radial velocities at the Hale telescope, but less on the imaging front.
So that's not one of the things you do. I'm really curious about. It sounds like you do get to go to South America to observe, and maybe Hawaii, and
yeah.
And I'm curious what that experience is like. You know, actually in the observatory, doing your work. So if you could describe that a little bit, that'd be neat.
Sure. Yeah, so I'll leave up this image here. It's definitely a nice, awesome privilege to be able to go to the observatories and really experience observing firsthand through them. I'll say that the actual act of observing is much different than it was 100 years ago. We're in front of like 10 different computer monitors typing, operating computer systems that are actually doing the observing. They're like running the electronics and the telescope and things like that for us. But definitely being there is an experience. You get to really appreciate the sky. All these telescopes are in world premiere night observing sites. They have really dark sky, really good image quality. You can go out during long exposure. You can go outside and take a look, and it's really breathtaking. Also, just it's nice being there. I'd say so. Currently, because of the pandemic, I'm observing from my apartment basically. So that's what I'll be doing in an hour. It's definitely not the same experience as being physically there, really appreciating the quality of the astronomical site that you're at.
Have most of the observatories opened back up, or what's? I mean, I know with Palomar, it's still. They are operating now, but they're certainly very limited in access to the facility. And
yeah, I would say that some have opened and some are starting to open is the current status. So the ones in Chile are like Gemini South is really closed still for nominal operations. They're like warming back. They're like trying to get back started. So but they're not back into full science operation mode yet. The ones in Mauna Kea were actually quite fortunate just because Hawaii is an island and it's a little bit much easier to kind of contain a pandemic on an island. So they were able to open much earlier. So I think CAC resumed observing back in June. So we've been able to observe since then. So I would say it's mixed. So some places are opening up or trying to open, and some places have opened depending on the situation.
We got some more questions?
Oh, I do see that. Let's see. Can you say a few words about adaptive optics technology? Will it ever get small enough and inexpensive enough for us amateurs? Clearly, certainly atmospheric turbulence is the bane of solar system planetary imaging. I think not in it. It seems unlikely to me in the near term that it will get inexpensive enough for amateurs, just because there's really no market for this technology other than maybe some like military purposes. So there's like astronomy is like a really big driver in developing in creating the technology possible for adaptive optics. It's a lot of these things that we use, like I was talking about these glasses that we change every millisecond or so. These are hundreds of thousands of dollars to buy a single device. So it's just we don't have the right economy of scale, I think, in that sense for adaptive optics. Maybe yeah, I'm thinking if there's possibilities for making this more consumer based, but it seems unlikely in my opinion. But I don't know if there's any promise in that category. Let's see. That's another question. How did you know which stars to look at to get these pictures of exoplanets? That's a great question. So a lot of times we have no idea. So at Gemini South, using this instrument, the Gemini Planet Imager, we actually did a blind survey of 600 stars. And this lasted about 5 years, where we picked what we think are the best stars. So these stars are close to us so that we can see things. We can actually separate the planet from the star. These stars are relatively young, so that these planets would be bright, still emanating heat from their formation. And we basically just did a blind survey of these 600 stars to look for these planets. And we got lucky on a few stars, and we discovered some planets, and we studied them. That's basically how these are found. So we try to make an informed decision, but it still requires some sort of blind survey to discover these stars.
So you're basically doing both the discovery as well as the characterization of them, huh?
That's right. That's the nice thing with having a spectrograph in the back of your instrument, is that you can, not in addition to just getting images, you can do spectroscopy.
But now the test satellite is detecting a lot of fairly close planets around close stars, fairly close stars, and of course they're transits. So if you were to observe the planets of the transiting planets around a star, then you would get a straight line kind of observation. But you still could, given that the planet was far enough separated from the sun, you still could get images of the planets, right? With a transiting planet.
So none of the current ones are possible of the transiting planets, because one, just because they're really compact. Like these transiting planets have orbital periods of like days, so they're within the orbit of Mercury, whereas we're talking about planets outside the orbit of like Jupiter and Saturn. So it's still a little bit too close for us. And also generally the test satellite, except with some exceptions, finds planets around pretty relatively old stars. And for these stars, these planets are much cooler, which again makes the brightness ratio harder. So the combination of the two usually puts it outside of our detectability range. I will say that actually just last month, we made the first detection of a radial velocity discovered planet. So a planet that was discovered indirectly through radial velocity means actually around 3 AU, so a little bit closer in Jupiter. We were actually able to take a direct image of it, and that's at least technically a big achievement in the field, because just doing these characterization of these indirectly discovered exoplanets is I think where the field is headed right now.
Yeah, so your ability to get to the hot Jupiters in the close things is not going to happen anytime soon.
Not happening anytime soon. People are actually working, work on other ways to study their atmospheres, either through transmission spectroscopy or through other spectroscopy methods. So it's not like they're out of the scope of direct imaging. Is not the only way to study their atmospheres. It's one of the only ways, perhaps one of two ways. But there's other ways to study the really close-in planets. So we're kind of complementary in studying the further out planets.
Yeah. So what time do you start observing tonight?
I start observing in an hour. So I probably need to sign off soon because I need to do some last minute prep work before I go on Sky. But yeah, with the time zone difference, the 3-hour time zone difference, the sun is just starting to set in Mauna Kea.
If you needed to just share your screen of your work, we'd be happy to sit quietly in the back and watch.
We promise not to kibitz.
Unfortunately, we also use Zoom, so I don't know if I can open like 2 Zoom sessions to share one with you guys and also connect to the observatory and things like that. But everything nowadays is on Zoom.
Yeah. Well, if people don't have more questions, maybe we should let Jason get on to his next project for tonight. Any more questions?
Thank you.
Yeah, thanks for having me. I really enjoyed it.
Yeah, it's very interesting to see how some of the real science is done on exoplanets and
so I guess one more question. What can amateurs do to help professionals? Do you have any amateur professional collaboration? Of course, Scott knows about that, but besides Tess.
Yeah, I'd say the test ones are definitely the easiest for amateurs to get involved in. Like I said, with direct imaging, we're very much dependent on having the largest telescopes, having the state-of-the-art technology that it's like we're really at the cutting edge of things. I think yeah, following up the transiting planets is probably the best way for amateurs to get involved in exoplanet studies. The other methods just require a lot of engineering before you can have a telescope that is like good enough to contribute to things, I think.
That brings up another question in my head. Do you know Rob Zellum?
Yeah, I do. I don't interact with him very much, but yeah, I do know.
You know who he is, right?
Yeah.
Rob's developing a piece of software that will let amateurs contribute to the certainty of the orbit predictions for transits.
Yeah, I heard him recently give a talk about this. Actually, a really cool initiative, I think.
Yeah, and we're actually working with Rob a bit too to help him help him verify his software and get it operational. So
yeah, that's cool. Awesome to hear that you guys are involved.
Yeah, that's another thing we can be doing with some of your colleagues at Caltech.
Mm-hmm. Yeah.
Okay, well, if nobody else has further questions, let's let Jason get busy and do some observing. That sounds like fun for him.
Yeah, I have another 12 hours ahead of me.
And I don't have anything else for this evening, so maybe we'll just call it a night. And thank you very much, Jason. That was very, very interesting.
Great. Well, I'm glad you guys liked it. Thanks for having me. It was fun. It's nice to talk about my research sometimes.
Yeah, very good.
Thank you very much.
Great. Thanks.
Thank you,
Have a good
Jason.
night, everyone.